Okay. Where are we? 7-16. Oh, okay. So I did the functions, the features of bone. Did I talk about this part here, the features, the diaphysis, and red bone marrow? Okay. Once again, let me just stress the epiphyseal plate. That's your growth plate. You will definitely see it on your next exam. Throughout Chapter 7, there are several places where they actually mention the epiphyseal plate, the area of hyaline cartilage that separates the marrow spaces of the epiphysis and your diaphysis. We're about to look at bone growth of a metacarpal bone, which is called endochondral ossification. And it's going to mention how once the cartilage is completely gone from the epiphyseal plate, that there's going to be the fusion of the diaphysis with your epiphysis, where they're going to kind of join together. So when they join together, it's going to leave behind a line, and that's when you stop growing. Okay. Growth stops late teens, early 20s is in your textbook. Okay. So I think we're here. The different types of bone cells. There are 4 types you need to be familiar with. You have your osteogenic cells, your osteoblasts, your osteocytes, and your osteoclasts. In your textbook, on page 210, exactly. On page 210, your osteogenic cells, the first cell that you see, guys, of course, is your stem cells. Those are the cells, they actually respond to any type of fractures. And what they do, those cells can transform themselves into your osteoblasts. Your osteoblasts are considered your bone-forming cells. They're the ones that are responsible for depositing matrix, osseous tissue, or more bone tissue in our bones. Okay, those cells, the osteoblasts, do not divide, so they don't go through the stages of mitosis. The osteoblasts will mature and become an osteocyte. An osteocyte, of course, it's also responsible or aids in the repair of fractures as well. It has a lot of functions to it, responsible for mineral deposition, maintaining the calcium concentration in our blood. The osteocytes, they have strain sensors, put strain sensors in our bones. So they are mature osteoblasts. Right below that, now if you look, osteogenic cells, your osteoblasts, and your osteocytes, they're all from the same generation or the same lineage, okay? However, your osteoclasts, which are just a bunch of stem cells that fuse together forming one dominant cell, which is your osteoclast, those cells are from the same line as our white blood cells, okay? The macrophages, the monocytes, the lymphocytes, and things of that sort. Osteoblasts, osteoclasts are responsible for bone remodeling. We're going to talk about bone remodeling in this chapter. Bone remodeling continues throughout life. Okay, it's just a regular part of bone maintenance, bone remodeling. So here you have it. They have each one listed in their major duties. I mentioned your osteogenic. They come from the mesenchymal cells, which we talked about in Chapter 5. Mesenchyme, of course, can give rise to any type of cartilage in the body, any type of tissue, because they're considered stem cells as well. Osteoblasts, please remember that they are your bone-forming cells, all right? as I stated earlier, they do not divide, okay, and they're responsible for depositing minerals such as calcium, phosphorus, sulfate, magnesium in the matrix of the bone in order to make it more calcified or to harden it, okay. If you look on page 209 of your textbook under osteoblasts, as I stated earlier, stress and fracture stimulate your osteogenic cells to multiply more rapidly and quickly generate increased numbers of what? Osteoblasts, which reinforce or rebuild what? Bone. There's a hormone associated with the osteoblasts as well. This is something new that they put in this textbook. Of course, it was not in the edition before this one, which is osteocalcin, okay? Responsible for increasing the amount of insulin, in the pancreas. You have osteocalcium, osteocytes. Like I said, these were former osteoblasts, but they're really mature osteoblasts, but they've changed the name and they're calling them osteocytes. I think the lab you guys did last week, they had a picture of the bone where you actually had to label the central canal, the canaliculi, the lacunae, the lamella, things of that sort. Now, the osteocytes, they're housed inside of that first bullet, the lacunae, okay? Those little areas inside of the bone, our bone, if you take a section of our bone, you cut it open, it's going to look just like that picture that you guys saw in your lab manual. So these are your osteocytes. They're housed inside of the lacunae. Canaliculi are little thin-like projections that run from one osteocyte to the next, kind of like a gap junction, connects the lacunae, and you have cytoplasmic processes that reach into the canaliculi as well. Okay. If you look at the first function, they reabsorb what? Bone matrix. Okay. One main thing that you need to remember about your osteocytes, guys, they're engaged in the metabolic exchange, all the exchanges of calcium and other minerals that have to take place. These are the ones that are engaged in the metabolic exchange with the blood. If you will turn over to page 210, I mentioned gap junctions there. That's at the very top. Some resorb bone matrix, and others deposit. Bone resorption, what we're going to talk about a little bit later, is resorb. Some reabsorb bone matrix. What happens is any new minerals in the blood will actually be absorbed and deposited inside of our bone matrix or the bone itself. The osteocytes are responsible for that. Any type of old minerals that have to be removed, okay, the osteocytes are involved in moving that as well. Contribute to your homeostatic mechanism of bone density and calcium and phosphate ions. It regulates the amount of calcium and phosphate ions in our blood, which is a really, really essential function. And it's also essential, or is responsible for maintaining our bone mass, which is very important as well. When stressed, produce biochemical signals that regulate what? Bone remodeling. Okay, we have what you call strain sensors on our bone. Last week, okay, this is your femur here, all right? This bone right here, which is our thigh bone, most of our body weight is placed on this bone right here, okay? So when, like for example, if you're starting to gain weight, okay, most of the stress, guys, is going to be here, okay? Now right here in the middle, like midway of the shaft, this part right here, that's where all the strength is. It takes a lot of force to break this bone right here. This is the strongest bone in the body. The only way this bone will break is if someone tackles you from the lateral aspect of it, and it will actually fracture it or break it. but it has to be a really, really strong force, like a football tackle or something. You know what I mean? So in your textbook, perhaps even more importantly, this is on 210, guys, the paragraph above number 4, your osteoclasts, they are what? Strain sensors. When a load is applied to a bone, it produces a flow in the extracellular fluid of the lacunae and canaliculi. This apparently stimulates the sensory primary cilia on the osteocyte and induces whatever. It's a lot of stuff. Remodeling, adjustments in bone shape and density to adapt to what? Stress. So any type of stress is placed on this bone, the osteocytes is going to help the bone to adapt to any type of stress, like I said, weight gain, weight-bearing activities. If you look on page 213 of your textbook, they're actually showing you the lines of stress. Figure 7.5, which is this bone here, the femur. They're showing you the red. Well, the red is your spongy bone, and of course, they're showing you the line of stress actually for both the spongy bone. Well, you have the spongy bone. So they're purple and what? They're red. So this is the greater trochanter right here. So right here, this is where all that stress is on the lateral aspect of it. Then you've got the head right here. You've got stress going down both sides. So the lateral part here, the proximal part here, this is where all the stress is what? Placed. The bone has to adapt to all of that stress that's placed on it. You know, sometimes that bone can only take so much stress. Now, it can support a lot of our body weight, but at times when the body weight is a little bit too much, it's a little bit too much stress on this bone, and of course, this bone may break or ache a little bit. Okay, so it's really thicker where you have the stress. It thickens here and it thickens here. Wherever you see those stress lines, that's where that bone gets really, really thick. And your osteoblasts are responsible for adding to or making the bone more dense. That's what it does. It becomes more dense, which means it's heavier, it's thicker, it's more pliable. All right. So the stress lines make the bones stronger. So when stress produced by hold all questions till the end. I'm recording my see, now I gotta pause it. Okay. So yeah, lines of stress found in the ends of what? The lateral proximal aspects of what? The femur. Okay. Osteoclast, another bone involved in bone remodeling. They're your bone dissolving cells found on the bone what? Surface. Guys, if you look up there, these bones, they live in what you call resorption bays right here. And what they actually do, they're multinucleated. Look at the organelles they have. They have lysosomes. You guys learned that in basic biology. They are multinucleated. Remember that. This is the only out of the 4 bone cells. This one right here is the only one that's multinucleated because it has a lot of nucleus. So they eat their way. Your book says they etch their way into the bone, and that's where they actually live. Okay. They develop from the same bone marrow stem cells that give rise to your blood cells. I mentioned that earlier before I started talking about each one of them. So the white blood cells, these are the ones that come from what? The white blood cells. Different origin from the rest of the bone cells. They're unusually large, and they have what? 3 to 4 nuclei, and sometimes they can have up to 50 or more. Like I say, these are some other functions right here. Resorption efficiency. We're going to talk about bone resorption a little bit later. Osteoclasts live in your resorption bays. Remodeling. results from combined action of your bone dissolving osteoclast and your bone depositing what? Osteoblast. Okay? So when they eat their way, or they etch their way into bone, we're about to talk about bone resorption. There are two. There's an enzyme involved and there's an acid involved. So when they release that acid, that's how they're able to kind of eat their way into the bone and just kind of live there. These cells, guys, they're really not our friends. We're going to talk about why a little bit later. Okay? On page 210 of your textbook, you may want to highlight that last sentence under osteoclast. Bone remodeling results from combined action of these bone dissolving osteoclasts and bone depositing what? Osteoblast. Okay? Once again, bone remodeling occurs throughout life. It's just a regular part of what? Maintenance of what? Bone. So, yeah. So you have your organic matter, guys. Your organic matter, which is, you have a polymer and you have a ceramic, okay? The polymer, guys, is collagen. Remember that collagen, which is the most abundant of all of these, the organic matter, which is synthesized by your osteoblast. And then you have these other components here, the protein complexes here. The main producer is really responsible for making the bone hard. Of course, is 85% hydroxyapatite. Hydroxyapatite, they're little calcium crystals that are formed in the bone. 10% of the inorganic matter is calcium carbonate. These other minerals are considered trace minerals, as you can see, as I stated earlier. Sulfate, fluoride, sodium, potassium, magnesium, they're only needed in what? Just a small amount or in a trace amount. Okay? That hydroxyapatite is really the inorganic matter that makes the bone really hard. The bone has to reach what you call a solubility complex, okay, of this hydroxyapatite, and then those little crystals are going to form, and it makes the bone more calcified, because when the bone is calcified, the bone is what? It's hard, right? Okay, so as the bone becomes really hard, it's flexible, it's bendable, it's pliable, okay? So, crystals of salt. Now with your collagen, you're going to get more flexibility with this one right here. Your collagen, you're going to get some degree of flexibility. Not a whole lot, but some degree of flexibility. Composite, which is in your textbook, you need to highlight this word here. You probably heard bone composition before. If you've been to an orthopedic doctor or something, they always talk about your bone composition or your bone composite. Bone composite, those two things I just mentioned to you earlier. The hydroxyapatite and the collagen. Combination of two basic structural materials. The ceramic portion, which is your hydroxyapatite, and your polymer, which is what? Your collagen. Okay? So bone combines the polymer collagen with the ceramic, hydroxyapatite, and other minerals. Ceramic portion allows the bone to support the weight of the body. That's your hydroxyapatite. And protein portion, as I stated earlier, gives the bone just a little bit, some degree of what? Flexibility. Okay. Now, remember this bone right here supports the weight of the body. Okay. The ceramic portion allows the bone to what? Support the weight of what? The body, which is your hydroxyapatite. Okay. So, if in this bone you don't have the hydroxyapatite, you don't have those, you're deficient in those other minerals or the calcium salts, the bone that you guys had in lab last week, you soaked it in vinegar, right? Okay. Now, if there's no hydroxyapatite in that bone, the bone becomes decalcified. And those other minerals, the bone becomes really soft. And it's going to become more bendable. Your book talks about rickets, okay, as the example. Rickets, which is on your next test. Soft bones due to deficiency of what? Calcium salts. What are your calcium salts? Hydroxyapatite. Rickets. Let's look at that. When the bones are deficient in calcium salts, guys, this is on page 211, that second column at the top. They are soft and they bend what? Easily. One way to demonstrate this is to soak a clean, dried bone, such as a chicken bone, in vinegar for a few days. As the mild acid of the vinegar dissolves the minerals away, the bone becomes flexible, it becomes rubbery, it becomes soft, it's bendable. You guys noticed that last week. It's pliable, it's really, really weak. Kids that have rickets have really, really weak what? Bones, and their legs tend to bow. You know, the femur, the tibia, and the fibula. Well, not the femur, but the tibia and the fibula. The legs take on a bowed effect. I don't know if they have this in this chapter, but the next chapter they do, because the weight, all that weight on those bones, because they're so soft, they're gonna bow out a little bit. Okay. As the mild acid of the vinegar dissolves the minerals away, the bone becomes flexible and rubbery. Such mineral deficiency and flexibility are the central problems in the childhood disease rickets, in which the soft bones of the lower limbs bend under the body's weight and become permanently what? Deformed. Okay? So, permanently deformed. And we're going to talk about rickets again a little bit later when we get into homeostasis and talk about the different hormones that are involved in maintaining the calcium concentration in the blood. Rickets, of course, is due to a vitamin D deficiency. Kids that are in third world countries or those underdeveloped countries, they're more prone to getting rickets. They don't have a lot of milk in those countries. Rickets is not common over here. I mean, we got plenty of vitamin D over here. Now, if people utilize it, that's really on them, because vitamin D is really, really important, responsible for, it really absorbs calcium. And I tell people, a student was telling me that her doctor has her on a calcium supplement, and I said, well, you have to be really careful with calcium or a calcium supplement. It can make you constipated. Has anybody taken a calcium supplement in here? That's why you really should take it with vitamin D, and the vitamin D with the calcium, you know, because the vitamin D is going to help the calcium to be to absorb quicker. All right, but just calcium alone, I'd rather drink the milk and eat the green leafy vegetables or whatever with the calcium. Drink the orange juice, eat the oranges, things of that sort. Osteogenesis imperfecta, guys, is a little bit different. Brittle bone. It's called brittle bone disease. That's when your bones really break under stress or they fracture when there's stress applied to it. That's when you don't have the protein. Without protein, a bone is excessively what? Brittle. Okay? So you got a collagen deficiency going on here. People are born with osteogenesis imperfecta. I had a student a couple of semesters ago say she was born with it when she was a child, and she couldn't really spend a lot of time on the playground playing with other kids because any little thing, she was always in the doctor's office because she had a fractured bone. All right? But as she started getting older and she started, you know, taking the calcium supplements, the vitamin D, she wasn't as prone to getting those fractures because, I mean, the bone is still developing, as we're going to talk about a little bit later, while you're growing in kids. So, brittle bone disease. Excessively brittle bones due to lack of what? The protein collagen. Okay? So this is that picture you guys had to label, I think, last week. For your lab. Nutrient foramina. It's just a little hole in the bone, a foramen. When you see foramina, F-O-R-A-M-I-N-A, that's just really a hole in the bone where nerves and blood vessels actually travel through. Perforating your Volkmann's canal, perforating canal right here, which is also called the Volkmann's canal, is going to intersect or bisect with the central canal. That's where you have your nerves, your arteries, and your blood vessels going on there. Any type of nutrients that have to get these little dark spots here, which is the lacunae, what's inside of your lacunae, your osteocytes. Any type of nutrients, oxygen, things of that sort, has to travel by way of the perforating canal to the central canal in order to nourish these osteocytes. Any type of waste that's removed is going to travel through the same route. Okay? In your textbook, read Compact Bone. You can just read it in your spare time. Yeah. I will mention this. Let me go back. That collagen is here. Okay. They pulled out 3 little sections of the lacunae. Okay. The central canal. If you look at these little striped lines, they're alternating right, left, right, left. That's those collagen fibers. And the reason they're alternating like that, that's what gives that bone that added strength. That makes it really, really strong. Those alternating, looks like a little corkscrew as your book describes it, of the collagen. Okay. Spongy bone. Don't have a lot about your spongy bone. Slivers of bone called spicules. If at the beginning of the chapter, they had that nice picture, chapter 7, that first page of spongy bone, those little slivers that you saw, those are called spicules. Then plates of bone are called what? The trabeculae. Of course, the reason you have those little holes, the spicules, the trabeculae, and things of that sort, and you have spongy bone, because red bone marrow has to occupy that area. Okay? So you have those little holes, and those little holes will be your red bone marrow. Does that make sense? Red bone marrow. If you go back to the bone where the distal end of the epiphysis is showing you what? The red bone marrow. Now, although that spongy bone, it looks like a sponge, we tend to think it's lightweight, but it's really, it lightens the weight of the bone, but it's hard because it's calcified as well. Okay? Provide strength with minimal weight. Strength with minimal weight. It lightens the weight of the bone. Develop along the bones what? Lines of what? Stress. Okay? Lines of stress. That's where the bone is strongest. Okay? Yeah, they just got a little bit of information about that. And this is what it looks like. It kind of looks like Swiss cheese, right? You see the little spicules? Oops. Bone marrow. Okay. That skeleton that you see wherever it's red, that's where your red bone marrow is. Okay? You've got your skull, the vertebrae, your ribs, your sternum, the hip bones or the pelvis. And look, and then you've got the head and the neck of what? The femur. That's red. And you've got the head of what? The humerus, which is this arm bone up here, that's red also. Bone marrow, general term for soft tissue that occupies the marrow cavity of a long bone in small spaces amid the trabeculae of what? Your spongy bone. Rest of that bone that has no color to it, that's yellow bone marrow. I think this word is on your next exam, hemopoietic tissues. Hemopoietic or hemopoiesis, of course, is responsible for forming all of the blood cells in the body, your red blood cells, your white blood cells, as well as your platelets. As I told you earlier, the second bullet or the second bullet, they're showing you where the red bone marrow is found, that I mentioned to you earlier. And when we reach a certain age, guys, that red marrow is going to be completely gone. In adults, we only have the yellow marrow. The yellow marrow is just fatty tissue. That's that adipose tissue, okay? Earlier, when we talked about the general features of the bone, we saw the yellow bone marrow housed in the what? Diaphysis, or the marrow cavity. It no longer produces blood. However, the yellow marrow can convert back to red marrow in extreme cases. Like, for example, if you're anemic, your textbook mentions that, how yellow can revert back to what? The red marrow. Ossification or osteogenesis, the formation of bone in the human fetus and infant, bone develops by two methods. Okay, on page page 214. There are two ways or two methods that bone form: intramembranous ossification as well as endochondral ossification. I don't talk about intramembranous ossification, but you do need to know what bones were actually formed by intramembranous ossification. The clavicle or your collarbone is formed by intramembranous ossification. The bones of the skull, of course, were formed by what? Intramembranous ossification as well. And I think the sternum, your book doesn't mention it, but the sternum is actually formed by that first one, intramembranous ossification. I do talk about endochondral ossification. The majority of our bones develop by way of endochondral ossification. Bone development starts at what week? I'm asking y'all a question. When does bone development start? Anybody pregnant in here? You need to know. It's in your book. That's going to be on your next test. 6 weeks. Yeah. So the fetus, the bone does not start translating from cartilage, because remember, at the beginning of the chapter, one of the functions, or it mentioned something about cartilage is the forerunner for bone, okay? You're going to have cartilage first, and then bone formation starts around 6 weeks. Even when the baby is born, there's still cartilage there. The bone has not completely ossified or transformed totally some of those bones into bone. So you're going to still have cartilage even there, even when the baby is what? Born. Okay. Endochondral ossification, page 214, is a process in which the bone is preceded by a hyaline cartilage model that becomes replaced by osseous tissue. It begins around the 6th week of what? Please highlight that in your textbook. 6th week of fetal development and continues into a person's 20s. Okay? Most bones of the body develop in this way, including the vertebrae, your ribs, well, this is your sternum. Parts of your sternum does it by intramembranous ossification. Scapula, your pelvic girdle, and bones of what? The limb. Then it goes on to talk about that epiphyseal plate, right? The growth plate. This is intramembranous ossification. The process is pretty much the same. If you read intramembranous ossification, it's going to pretty much say the same thing that it says over here. Okay, now they've taken a metacarpal bone, they're showing you a little picture of the metacarpal bone in the hand of that little baby. Okay? Early cartilage model, nothing but hyaline cartilage. If you look at your marrow cavity, well, it's not the marrow cavity yet. Okay? This middle portion right here, this blue, all of this is just what? Cartilage. Around the hyaline cartilage, you have what? Perichondrium. What does perichondrium mean? What does perichondrium mean? Y'all can't ask me questions, but I can ask y'all questions. Around the heart. Perichondrials means cartilage, right? It's around the hyaline cartilage. Pericardial means around the heart. What's the term used to describe around the bone? That's on your next test. Periosteum. It talks about periosteum in this chapter, doesn't it? Okay. So here you have it, guys. This is called it's not called the marrow cavity yet. It's called the primary ossification center. Okay. What's going to eventually happen is right here, your osteoblasts are going to start forming here. That perichondrium is going to become the periosteum. Because if you look right here, this little tan section, bone formation has actually already started. You see that little bony collar? It's called collar of bone right here. These chondrocytes, which are your cartilage cells, because the matrix starts to get hardened or harden, the chondrocytes are cut off from the nutrient that they were once getting, and then they're going to die. So these chondrocytes right here, they have to die, okay? So you have your bony collar. Now we have the periosteum. We don't have the perichondrium anymore now, right? Okay. Now if you'll look closely, this one right here, look how that cartilage is eroding or breaking down. The osteoblasts are coming in, depositing bone in the matrix. The osteoclasts are coming in behind it. Any cartilage that's being broken down is going to erode it, and just get it out of the way. So that's what's going on right here. Now you have this hollow space. Now they can call it the primary marrow cavity. It's not called the primary ossification center anymore, right? Although they mentioned blood vessels over here, you've got blood vessels invading the marrow cavity over here as well. Okay. Vascular invasion, formation of a primary marrow cavity, and the appearance of your secondary ossification center. Now, same thing is about to occur here in the epiphysis. This is your secondary ossification center. Remember, the shaft is the primary ossification center. The epiphysis here and here are known as your secondary ossification center. Okay? Same thing will occur here. Chondrocytes have to die because they're cut away from the nutrients. And now this becomes your secondary marrow cavity. So you can see they're changing the names for you as well. Now you have the epiphysis, you've got the metaphysis, you've got your diaphysis. Now look at this one right here. This is what the bone typically looks like at birth in a baby. Now, there's still a secondary ossification center here that's lagging behind even at birth. Remember I told you guys there's still going to be some cartilage there. Everything is not going to be bone yet. Bone at birth with enlarged primary marrow cavity and appearance of secondary marrow cavity in one, it didn't say two, in one epiphysis. If you look, what number is that? Number 4. Let's look at number 4. Someone read number 4 for me, where it says the secondary, start at that paragraph above it where it says soon chondrocyte enlargement and death occur. Now everybody read at the same time.
Soon chondrocyte
Mm-hmm.
model as well, creating a secondary ossification center. In the metacarpal bone, as illustrated in Figure 7-9, this occurs in only one epiphysis in longer bones of the arms, forearms, legs, and thighs. It occurs at both ends.
What's your name?
Amber.
Amber. Okay. So the metacarpal bone. Well, you'll know where the metacarpal bone is by next Saturday. Like your knuckles. This is the head. The heads of the metacarpal bones are your knuckles. So it's like they start here at the wrist or carpal bones and they go here. Okay. There's only one secondary marrow cavity, right? And then you've got the secondary ossification center that's left behind. But like she just stated these long bones, you're going to have what? A secondary marrow cavity in the femur, the tibia, the fibula, the humerus, the radius, and what? The ulna. Okay? Read number 4, Amber.
The secondary ossification center becomes hollowed out by the same process as the diaphysis, generating a secondary marrow cavity in the epiphysis. This cavity extends outward from the center in all directions. At the time of birth, the bone picture looks like step 4 in Figure 7-9. In bones with two secondary ossification centers, one center lags behind the other in development. So at birth, there is a secondary marrow cavity at one end, while chondrocyte growth has just begun at the other. The joints of the limbs are still cartilaginous at birth. Figure 7-10.
Yep. Still got cartilage in the femur, the tibia, the fibula, the humerus, the radius, and the ulna. Because remember, these bones have a secondary ossification center at both ends, the proximal and what? Your distal end. Okay? Now, look at number 5. Bone of a child with epiphyseal plate at the distal what? End. At the distal end. At the distal end. Or is that the proximal end? I think there was an error here. So you have the epiphyseal plate there. Remember the epiphyseal plate? There's still like little remnants of cartilage, as you can see there. Okay? Now this metaphysis or metaphysis, however you want to call it, it just depends on where you're from. That's the transitional zone of the epiphyseal plate. Okay? That's when the cartilage actually starts transitioning into what? Into bone, as you can see. So you have your epiphyseal plate. The bone is still growing, right? Because you still have a little bit of what? Cartilage here. Okay? Bone of the child with the epiphyseal plate here. Now, this is what an adult bone looks like. Now the bone has stopped growing. We're in our 20s. You're 20 years old. The bone has what? Stopped growing. Okay? And, of course, this is what it looks like. Now, you've got all of these features here. You've got your spongy bone. You've got your blood vessels, the little hole, the nutrient foramina, the spongy bone at the other end. The epiphyseal line is going to be left behind when you stop growing, right? But in order for the epiphyseal line to, remember this, in order for the epiphyseal line to be left behind, that cartilage has to be completely gone. And step number what? 5. There has to be no cartilage there in order for the line to be left behind. Okay? So those kids that are, look, these 3-year-olds that are playing football, not good. Their bones are still growing. Okay? Be careful. So what's at the end now? We still got cartilage here, but it's called the articular cartilage. Remember in chapter 5, we talked about elastic cartilage, fibrocartilage, and hyaline cartilage, right? Hyaline cartilage is found at the distal ends of what? Bones, long bones, right? Okay, the hyaline cartilage now is articular cartilage. So, why do you think cartilage is just left behind at the ends? We're going somewhere with this, people. Why do you think? Why do you think there's cartilage still here? Okay, I can deal with that. But that's really not it. Okay. So you're right. Thank you very much. Remind me to give you 2 points on this test for answering. I think isn't it in your book? Y'all looking at me, waiting for me to give you the answer, right? Haven't y'all learned me by now? I want you to look in the Anatomy Bible, the most expensive book in the bookstore. Costs more than the class here. Amber, right? Amber. Well, is it? Where'd you see that? Look, is it in the book?
I just know that how you get arthritis is from the wear and tear of your car. Just like I learned in another place where like when you pop your knuckles, they say it wears and tears your car. So
that's a myth, by the way. We'll talk about it.
Arthritis comes from like the wear and tear of your
yeah.
car. And you have the car to keep the friction from your bones.
Exactly. It makes the bones more mobile. I think we mentioned that in chapter 5, and like she says, it decreases what? Friction between the bones. If this cartilage, we're going to talk about, good job, Amber, we're going to talk about rheumatoid arthritis in chapter, I think it's chapter 9, when we talk about your joints. A joint is a point of contact where 2 bones meet, okay? So if someone has cartilage, let's say our metacarpals and the phalanges, okay? So that joint between your metacarpal and your phalanges, if that articular cartilage has been completely gone or has eroded or is not there anymore, what's going to happen? Simple. Bone friction will occur. Bone will rub against bone. Very, very painful, okay? Little bone spurs will form, kind of looks like little jagged edges between the bone because they're just rubbing up against each other. And that's why people with arthritis are in so much pain. If you've got that articular cartilage missing, there's no synovial fluid. Synovial fluid lubricates what? The joints between the bones. So that synovial fluid is gone, the articular cartilage is gone, bone is rubbing up against bone. They're in a lot of what? Pain. Very good. I thought it mentioned it in number 6. By the late teens to early 20s, all remaining cartilage in the epiphyseal plate is generally consumed. No cartilage there, and the gap between the epiphysis and your diaphysis closes. The primary and secondary marrow cavities then unite into a single cavity, and the bone can no longer grow in what? Length. I thought that the reason I was asking you that, Amber, I thought that what you just said was somewhere in this chapter. Maybe not. Maybe I was thinking about chapter 9. Yeah, which we talk about. Makes sense? Endochondral ossification. Now, you know your next exam, I'm not going to ask you about all of these steps right here, but I may ask you the bones of the femur, the tibia, the fibula, blah, 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 formed by which type of whatever. You all know how I ask my question. And you would say, what, an endochondral ossification, what center? If I say the skull of the bones and the clavicle, the bones are formed by way of intramembranous ossification. Exactly. Epiphyseal plate, here you got it again, serves as a growth zone for what? Bone elongation. So in order for that plate to close and leave behind the line, what has to happen? All the cartilage has, remember that for your next exam, all the cartilage has to be what? Completely gone. So here, I think I mentioned this picture earlier, the little tan areas that you see on this developing fetus is still cartilage. The red part, of course, is now bone. This is what it looks like at 12 weeks. Okay. Ossification continues throughout life with the growth and remodeling of bones. Bones grow in two directions, in length and width. There are two terms to describe the growth of bone. You have interstitial growth and you have oppositional growth. The interstitial growth, of course, is responsible really for the elongation of the bone. Appositional growth, of course, the diameter and the width of the bone will actually increase due to appositional growth. These two terms are in your textbook on pages 218. They have interstitial growth in bold, and they have appositional growth in bold as well, under bone widening and what? Thickening. Okay. There's that epiphyseal plate again. I don't know why they keep bringing this thing up. Metaphysis is the zone of transition facing the marrow cavity. Okay, if you look at figure 712, look at zones 1. They're showing you zones 1 through 5. Guys, they're showing you all 5 zones right there in the epiphyseal plate. Now, if you look at zones 2 and 3, your chondrocytes, they proliferate, which means you're going to get a lot of them forming, and you're going to have, they're going to multiply as well. Now, if you look at zone 3, zone of cell hypertrophy, hypertrophy we know means enlargement. So your chondrocytes are going to enlarge in zone 3. Now, I brought this to your attention. Zones 2 and 3, guys, are responsible for the bone elongating. The long bones, the femur, the tibia, the fibula, the humerus, the radius, the ulna, or really the bones of the leg, actually. So when you grow taller or there's an increase in your height, it's due to zones what? 2 and what? 3. And as you can see, zone 4, that's when calcification occurs in zone 4. Okay, so zones 2 and 3 will actually remove that zone of reserve cartilage, which is in number 1. Zones 2 and 3 are actually going to remove it or push it out of the way. Yep, here they are here. It's a lot of zones. Interstitial growth, bones increase in length. Occurs at different ages. And so when people stop growing, the bones, the increase in length of bone, it's going to vary from individual to individual, and it's going to vary according to your age. Because, you know, some people are short, some people are really, really tall. Some people are average height, just as myself. Appositional growth, there's going to be a widening of what? The bone, because bone is going to be deposited on the surface. Bone remodeling. Wolff's Law. My favorite part of this chapter, besides talking about your osteoblast, your osteoclast, your osteocytes, and your osteoprogenitor cell, Wolff's Law is on your next test. Occurs throughout life, bone remodeling, 10% per year. Okay, let me just say this. Spongy bone in us gets replaced about 2 or 3 times a year. Compact bone, the hard part, never changes, but we don't replace it 2 to 3 times a year, probably at all. But we do replace the spongy bone 2 to 3 times a year. Bone, that's called bone remodeling. 10% occurs throughout life, 10% per year. Okay. Mr. Law states that the mechanical stress placed on it, on bones, adapt to withstand those stresses placed on it. Remember, we just talked about that. Those stress lines, that's Wolff's Law. Okay? The bone adapts to any type of stress that's going to be put on it. It has to. All right? There's no ifs and buts about it. What 2 bone cells are involved? Know this for your test. Osteoblast and your osteoclast. Guys, there's supposed to be a balance between these two right here. Okay. But based on your reading about Wolff's Law, which you will be reading because I'm telling you to read it, one is going to start outpacing the other. Okay. Bone formation kind of peaks at around 20. So if at age 20, if any of you are 20 in here and you want to start taking calcium and drinking a lot of milk and eating yogurt, drinking your orange juice or taking a supplement, that's okay. You can start at the age of 20 because that's when your bone formation peaks at that age. And then what happens is osteoclast starts stripping away at your bone, okay, leading to osteoporosis, all of those different diseases where people have weak bones, okay? And they start outpacing the osteoblast. The only way you're going to keep a balance here is if you are doing exercising. Students don't want to hear that. As is when you exercise, that's when your bones remain strong. Weight-bearing activities, lifting weight, walking, running, jogging, just a little bit. You don't have to do a whole, it says moderate, not severe. You don't have to overdo it. Just a little bit. Keep these bones strong. Bony processes grow larger in response to stress, mechanical stress. Okay? So what is bone remodeling? Those little hairline fractures. Has anybody had a hairline fracture in here? Little bitty tiny fracture. You don't even have to go to an orthopedic doctor to just repair itself. Release minerals into the blood. Calcium, phosphate. Okay? It's responsible for maintaining the blood calcium concentration, remember? That's bone remodeling. Reshapes the bones in response to what? Use, disuse. Not using them, using them. If you're using them, it's going to what? Deposit more bone. The bones become more what? Dense. So it can, bone remodeling, the architecture of a bone can change. The structure of a bone can change. All of that. All of that is bone remodeling. And it occurs when? Throughout life. Okay. Bone remodeling. A collaborative and precise action of your osteoblast and your what? Osteoclast. Okay? So it missed. I don't understand why. Bony processes grow larger in response to mechanical what? Stress. People that do manual labor, your book talks about it. Athletes, any athletes in here? They got very strong bones. Their bones are very dense, okay? Because they're doing a lot of what? Weight bearing, putting a lot of weight on them. That's making them dense. Your book also talks about if you are a couch potato. If you're a couch potato, what's going to happen? The osteoclasts are starting to eat away at your bone, and they just become weaker and weaker and weaker. And then some of y'all now probably, your knees are probably aching. Probably be aching when you get up in the morning. Can barely get out of the bed. Can barely get off the floor when you're down there playing with your kids. Would that be anybody in here? That's okay. Like, Has a lot to do with joints, has a lot to do with these bones too. We're going to put it all together in chapter 9. Okay? This bone right here, your book mentions. There are 2 parts. It's going to be on your exam next Saturday. The greater trochanter, which is this big, thick outgrowth here, and you have the lesser trochanter. Okay. Newborn babies, they don't have this. The minute those babies get up and start walking, and they put weight here, the tendons, ligaments, things pulling on it. That's a lot of weight on this. They start walking, that's when this forms. This one, than that one. Okay? Because they're putting what? Stress on it. So you're going to have this little outgrowth here. All right? Let's look at that. Because you really need to understand this part. Second paragraph, Wolff's Law of Bones. Someone read that for me. States that the architecture of bone is what?
Determined by the mechanical stress placed upon it. If a bone is little used, osteoclasts remove matrix and get rid of unnecessary mass. If a bone is heavily used or stress is consistently applied to a particular region of a bone, osteoblasts deposit new osseous tissue and thicken the bone. Consequently, the comparatively smooth bones of an infant or toddler develop a variety of surface bumps, ridges, and spines, described in chapter 8. As the child begins to walk, the greater trochanter of the femur, for example, see figure 7.5, also see figure 8.38, page 269, is a massive outgrowth of bone stimulated by the pull of tendons from several calf and hip muscles and sword and walking.
And read that top sentence on page 220.
On average, bones have a greater density in mass in athletes and people engaged in heavy manual labor than they do in sedentary people.
Yep. So if you're not doing any type of activity, and you're just going home, sitting on the couch, eating those Lay's potato chips, a couch potato, or eating a potato on the couch, you can see what happens. These bones get weaker over time. What's going to happen? Let me show you what can happen. Let's turn to page 228. Your spine is going to eventually start looking like that spine on page 228. Okay? They're showing you spongy bone, how normal spongy bone is supposed to look like, and how the osteoclast, if you look at that second picture, there's a big hole in the spongy bone. Looks like something, a rat or something has just eaten its way through it. Okay? That's because the osteoclasts are now starting to outpace what? Your osteoblasts. So the osteoclasts are just eating away at the bone matrix, removing bone. And that's what happens. So that old lady, she has the widow's hump. Your spine becomes compressed. If you look at letter B, the spine becomes compressed. And of course, letter C, she has a little widow's hump or kyphosis. And people with osteoporosis are more prone to fractures of the hip, this part right here, between this part here, okay, fractures. Just sitting down, not really sitting hard, can cause fracture of what? The spine, the distal end of the spine, the vertebral column, they get fractures there. Because like I said, what Amber just read, the osteoclasts start removing matrix. That starts at the age of 20 if you're not putting any stress on them. All right? Okay. So back on page 220, that last paragraph, the orderly remodeling of bone depends on a precise balance between deposition and what? Resorption. Deposition by your osteoblast, resorption by your osteoclast, between those two. If one process outpaces the other or both processes occur too rapidly, various bone deformities, developmental abnormalities, and other disorders occur such as osteitis deformans, which is Paget's disease. That one, of course, can lead to arthritis. That's when your bones are in a lot of pain. Very, very painful and deformed bones is Paget's disease. Osteogenesis imperfecta that I mentioned earlier, the brittle bone disease, where you're more prone to fractures and osteoporosis, which I just showed you a picture of, the spine of that lady, the osteoclast eating away at her what? Her spine. Okay? So we're going to stop here.